Advanced Math Lesson 40. Part A is called the argument. Argument can mean several different things depending on the context, and even in math, in different branches of math, it can mean different things. An argument, when we were studying logical statements, could also be considered or called a syllogism. That's when you told if the argument was valid or invalid, and if you could reach a conclusion. Those are arguments. These are different. These are going to be arguments of functions. So first we're going to review functions briefly. A function is a set of ordered pairs, like a set of points. If the same rule is applied to the first member of each pair, so like the x, to get the second number, then the first member can be called the argument of the function. So it's the input of the function, what you're putting in. Input of the function. Okay, so when we talk about f of x, x is the input, is the argument. Here we have some other functions. Y, or f of x, equals the logarithm of 100. Log of 100. 100 is the argument. That's what you're putting into that function, and then you could evaluate that and find out what y equals. Log, when there's no base written, is base 10, so 10 to the what equals 100. This would be 2. Y would always equal 2 for that, whenever the argument is 100. Okay, here the argument is x, the sign of x. You know, it's not times x or anything like that. It's the sign of x. You can't evaluate this unless you know what the angle is. That angle that you put in would be the argument. Here the argument is x plus 2. If the argument is more than one term, so it's like a binomial or a trinomial, then we put it in parentheses so we know that whole thing is the argument. That's not just the log of x, and then we add 2 to what we get. You add 2 to the x, and then take the log of that. So for this one, just for instance, if we were doing, if x equals 8. Okay, if x equals 8, okay, then we have the logarithm base 10 of 10. Well, 10 to what power equals 10? So it would be 1. Y would equal 1. And you could pick other values for x and put them into there. X plus 2 is the argument. Here, this is cotangent, and 2x minus pi is the argument. And again, it's not that it's being multiplied, it's cotangent of what? Sine of what? I don't think there's really much else we need to say about those right now. It's just so you're aware of what we're doing, I guess, in the next part, and then for the future lessons. In part B, law of logarithms. Okay, you hopefully recall logarithms are basically exponents. We can change back and forth between log form and exponential form. Okay, so I'm going to write that up here. We had back in, I think it was lesson 26. The logarithm base b of some number equals L, because the logarithm is whatever that is, so that's the L. This is the base, and that's logarithmic form, and we can change that to exponential. It's b to the L equals n. The logarithm is an exponent, and because of that, the same rules that apply to exponents apply to logarithms. So here in the box, we have a review of it says when you're multiplying and they have the same base, you add the exponents. Exponents are logs, so when we multiply, we add. That's what's down here. When you're multiplying, m times n is there, you add them. You can split them up or put them together, whatever is helpful in simplifying things. The quotient rule for exponents. When you're dividing and they have the same base, you subtract the exponents. So when you're dealing with logs, since logs are exponents, When you're dividing, you subtract. And then the power rule. When you have a power raised to a power, you multiply the exponents. So when you have a log to a power, you multiply. Okay? Which the m is to the power. But then you multiply. And then we're going to use those rules to simplify some things or solve some equations. Okay, so let's look down here at example 1. Okay, so I see here these all have the same base. Here's a log plus a log. Okay, so this part can be rewritten log base a, and when they're multiplied is when you add, right? So that means this is the same as log base a of 4 times 6, which is 24. Okay, and then we have this part's the same, log base a of x plus 4. That whole argument stays in the parentheses. Now we have log base a of something equals log base a of something. If those logs are equal to each other, then the arguments have to equal each other. So 24 equals x plus 4, and then we would subtract 4 from both sides and find out that x equals 20. Okay, now, this is important. The argument of the logarithmic function has to be a positive number. Okay, so there's one more step after you've solved. I'm going to write this. Argument of log function must be positive. Okay, it doesn't mean x has to be positive. It means the arguments of your functions have to be positive. So then we need to look back at the equation and make sure when we put x into any of those arguments that we only get positive numbers. And there's no x here, no x here. It's only there. If we put 20 in there, that's 24. So it's okay. That's positive. Okay, just make sure you check that when you're done before you say that's the answer. Okay, the argument has to be positive. So you put your value back in and check it. So we must check. So again, you go back to the original equation. X plus 4, 20 plus 4. That's definitely positive, so we know it's okay. Just don't forget to do that step. All right. Next example. Ooh, I stuck a fourth one over there. Okay, so for this one, I see subtraction here. That means we're dividing. So we have log base 4 of x plus 6 over x minus 1. You can look back at the rules. Okay, it's the first one over the second one equals log base 4 of 5. Same base, they equal. That means the arguments must be equal. So x plus 6 over x minus 1 has to equal 5. And then we solve it. To get this out of the denominator, we're going to multiply both sides by that denominator over 1. Okay, they cancel. So x plus 6 equals 5x minus 5 after we distribute. Okay, then I'll move x over there and 5 over there. And so we have 11 equals 4x. Divide by 4, so x should be 11/4. Now I just need to put that back in anywhere there's an x in the equation. Make sure the arguments are positive. Okay, so 11/4, I have a positive 11/4 plus a positive number. That one's good, that's positive. 11/4 minus 4/4 is 7/4, which is still positive. So that's fine. That's the answer. X equals 11/4. Okay, so we have two more examples here. And, okay, for this one, this is going to be using that third rule. This part right here, okay, that 3 is going to be the exponent to the x. Log base b of x to the third equals log base b of 8. Log equals log, they're the same base. The arguments have to be equal. So x to the third power equals 8. That means x has to be 2. And that's just, x is the argument. 2 is positive. We know that's fine. Okay, one more over here. And for this one, okay, what do we have? Oh, okay, so this 2/3 is going up there on the 64. Log base 12 of x equals log base 12 of 64 to the 2/3. Same base, the logs are equal, therefore the arguments are equal. And now we're going to simplify this. Okay, so the cube root of 64. What do you take times itself 3 times to get 64? That'd be 4, right? So x equals 4 squared. So I did the cube root first. And then 4 squared does 16. 16 would be the argument. It is positive, so we know that's fine. And that's it. We're done with part B. Part C, you've been doing this already. Okay, part C is about properties of inverse functions. And here you go. 2 functions, f and g, are inverse functions if, when you compose them both ways, you get x. F of g equals x and g of f equals x. When that happens, f and g are inverse functions. And you've already been seeing that happening in some of your problem set problems. So when it says in example 5, show that f of x equals 1/3 x minus 3 and g of x equals 3x plus 9 are inverse functions by computing their compositions, they're just telling you find f of g and find g of f, and by the way, they're both going to equal x. So you know what the outcome is supposed to be, you just have to do it. Okay, so over here I'll do fog. That's where I put g into f. So this whole thing is going in place of that x. So we would have 1/3 times 3x plus 9 minus 3. And then we simplify. Okay, so 1/3 of 3 is 1. This is x plus 9/3 is 3 minus 3. Look at that. We get x. Okay, then we do g of f of x, which is where we put f into g. So this whole thing is going in place of that x. Okay. And so that means 3 times 1/3 x minus 3 plus 9. So this would be, okay, distributing, we have 3 times 1/3 is 1, so x minus 3 times 3 is 9, plus this 9, the 9's cancel, and we get x again. There, we have shown it. Okay, that's all you do. Same thing you've already been doing. One more example. Whoops, I went too far. Okay, so for this one, same thing. Here are 2 functions. Show that they're inverse by computing their compositions. F of g, g of f. So, f of g, putting that fraction in place of that x, Well, this looks like fun. 1 over, and then copy G, 3x plus 1 over x minus 3. It's one of those. Okay, there's two fractions on the bottom, or two quantities on the bottom. We need to have common denominators, so we're going to go x over x times that one. And that means we have 1 over 3x plus 1 minus 3x all over x. The 3x's cancel, 3x minus 3x. So this is 1 over x. 1 divided by 1 over x is the same as 1 times x over 1. It's x. No surprise. G of f of x. Okay, so now we're doing it the other way. We put f into both of those x's. So 3 times 1 over x minus 3 plus 1 over 1 over x minus 3. Okay, so for this one, I kind of would have two different ways you could go about this. Let's go ahead and multiply that. We have 3. Actually, before I do that, I'm going to multiply x minus 3 over x minus 3 times that one. Okay, so now I have 3 plus x minus 3 all over x minus 3 over 1 over x minus 3. Okay, so in the top fraction, 3 minus 3, they cancel. So we have x over x minus 3. I'm running out of room, and it'll be easier to show you anyway if I do this. It's this divided by this fraction. When you're dividing by a fraction, you multiply by its reciprocal. Whoops, forgot the minus 3. So when I flip this fraction, I get this part. Okay, dividing by 1 over x minus 3 is multiplying by x minus 3 over 1. Cross, cancel, and it's x again. And we're done with the example and with the notes. Enjoy.